Hello everybody! What are differential equations? An ordinary differential equation, or from now on just a differential equation, is any equation using numbers and the letters x, y, y prime, y double prime, and so on. Hereby y is supposed to be an unknown function in x, y equals f of x. Y prime is supposed to be its derivative, f prime of x, or df over dx. Y double prime is supposed to be the second derivative, and so on. Examples of such differential equations are y prime plus y double prime times y equals 2 times x plus x squared, for instance, or y prime times y equals y prime plus e to the power of x. Now equations certainly ask for solutions. A solution of such a differential equation is any function y equals f of x obeying the equation. That means that for every fixed x, if we calculate the value y equals f of x of the function at that point, and also the slope y prime of f at x, and all values y double prime and so on, we get an equality. Or in other words, if we can express y by an expression, and if y prime and y double prime and so on are expressed by expressions too, then plugging in these expressions yields an identity in x, equivalent expressions on both sides. Let's look at the two examples above. The function y equals x squared is a solution of the differential equation y prime plus y double prime times y equals 2 times x plus x squared. Y. We plug in the defining expression x squared for y, as well as 2x for y prime and 2 for y double prime, and get the identity 2x plus 2 times x squared equals 2 times x plus x squared. For the second example, for every real number c, each one of the functions fc of x, defined by 1 plus square root of 2 times e to the power of x plus c, as well as each one of the functions gc of x, defined by 1 minus square root of 2 times e to the power of x plus c, is a solution. By the way, for negative c, these functions have a limited domain, each one a little different. Now to confirm the solution property, first we rewrite the differential equation as y prime times y minus y prime equals e to the power of x, or y prime times y minus 1 equals e to the power of x. Now note that by chain rule, gc prime of x is negative 1 over 2 times square root of 2 e to the power of x plus c, which is the outer derivative, times 2 times e to the power of x, which is the inner derivative of this composed function. And therefore, y prime times y minus 1 equals minus 1 over 2 times the radical times 2 times e to the power of x times negative the radical again, which is equal to e to the power of x, as desired. For the fc functions, the conformation is similar, just without negative signs. Some of these graphs for c equals negative 3, negative 1, 1 and 3 are displayed in the graph. Note that the graphs are usually not obtained from each other by shifting up and down. This second example also shows that almost always there are infinitely many solutions. But very often we are not interested in all solutions, but only in those solutions f whose graph goes through a given point x0, y0. Only those f where f of x0 equals y0. Then we have a so-called initial value problem. The name stems from the fact that x0 is often equal to 0, so the initial value f of 0 of the otherwise unknown function f is given. If we choose the orange point with coordinates ln of 1/2 and 1, about negative 0.7 and 1 in our example as initial point, so if we require f of negative 0.7 to be equal to 1, then we only have two solutions, 1 plus square root of 2 times e to the power of x minus 1, and 1 minus the same radical. Okay, all this was checking whether a given function is a solution of a given differential equation. This may not be too hard, Also, it is harder than checking a solution of an ordinary algebra equation, since you must differentiate the given function, maybe repeatedly, and you eventually have to check whether the two expressions are equivalent. But how about finding solutions? Well, if solving algebraic equations can be very hard, solving differential equations can be very, very hard. Even harder than that. Some differential equations are a little easier. One type is linear differential equations, which I will not discuss here. The other type are first-order differential equations, which are differential equations where only x, y, and y prime occurs, but no higher derivative. For first-order differential equations, there are two rather elementary tools available. One is a graphical method, the other requires integration. Be warned that even for first-order differential equations, they work only in some cases, not always. The tools are: number one, the graphical method uses a concept which is called direction fields. And number two, there's also a formal method which is called separating variables method. For both of these methods I also have videos available. First-order differential equations are equations in x, y, and y prime. If one of these letters is missing, things may become a little easier. First, if y prime does not occur, we have an equation in x and y only, where y is supposed to be a function in x, not a number. The function y equals f of x is given implicitly by this equation, just as in implicit differentiation, but the question is whether the equation can be solved for y. This is really just algebra, so such an equation would not be considered to be even a differential equation. Now, if y does not occur, we have an equation in x and y prime only. Provided we can solve this equation for y prime, we have an antiderivative question, the question to find an indefinite integral. Given is some expression defining the derivative of some function f, what expression defines f? Even such a request is already often very hard, sometimes even impossible to do. But this case is just ordinary antiderivative stuff. Now, if x does not occur explicitly in this equation, we call the differential equation autonomous. The law connecting y equals f of x and its derivative is the same for every x. This type tends to be a little easier to do. Okay, thanks for listening. Now you may want to proceed with one of the two methods.